everyone, I'm Chang and this is Foundations of Artificial Intelligence. Today I'm very excited to walk through a gentle introduction to entropy and information theory with y'all. The goal of this lecture is really to dig deep into the definition of these terms so that the next time you're at a talk or in a conversation when someone throwing around these buzzwords, you know what they mean. So these include entropy, microstate, macrostate, information gain, mutual information, Colab-Liebler or KL divergence, epistasis. And I will also discuss some applications of entropy and information theory in general in health and biomedical informatics. But first, a quick review of statistics, specifically expected value. Let's play a game. Say you toss a fair coin. If it comes up heads, you win $1, and if it comes up tails, you lose $1. The question is, what is the expected value of your winning? Now, without doing any math, you probably have guessed that you expected to win nothing because the coin is fair. If it comes up heads, which is probably going to be 50% of the time, you win $1, and if it comes up tails, you lose $1. Your chance of winning and losing is equal, so you expected to win nothing, and you would be right. Now, mathematically, if you put this in the formula for expected value, what you would do is taking the value multiplied with its associated probability. So in this case, you win, the amount of dollar you win is 1, and you will multiply that by 0.5 because the coin is fair. You have 50% chance of winning. And similarly for the loss, if you lose $1, you would multiply that -1 with 0.5. Summing both of these together, you get $0. Now, that's great, it's a fair coin. What happens if the coin is no longer fair? What if P heads now is 0.8 and P tails 0.2? Easy. All you need to do is plug it in the same equation, right? But instead of the 0.5s we have earlier for the probabilities, we now have a 0.8 for the +1 because that's the probability that the coin will come up heads, and then a 0.2 here. You end up with $0.6 at the end. So that's your expected winning after playing this game once. If you play this game n times, as n grows, the average across these times will almost surely converge to this expected value. So if you play this game 100 times, you're likely to win about $60. And this formula can be generalized into the summation of multiple terms. So let's say instead of having just 2 outcomes, win or lose, heads or tails, you now play a different game with a 6-sided dice, then you have 6 different outcomes, x1 through x6. The formula would still apply as long as you know the probability of each of these x's. And to shorten it, you're going to write this as the sum of xi times pi. All right, we're going to come back to this formula a lot throughout the lecture. So it is the expected value of the random variable x having the value x of I. Okay, so now what is entropy? You probably have heard of entropy as a measure of disorder or uncertainty or surprise. It has something to do with information. And I think the confusion comes mostly from it being used in 2 different fields, physics and also computer science and information. So let's go through the physics one first. First, some definitions. In statistical mechanics, a microstate is a specific microscopic configuration of a thermodynamic system. In contrast, a macrostate of a system refers to its macroscopic properties such as temperature, pressure, volume, and density. And when people talk about, oh, entropy always increases, and that's why when you pour milk in your coffee, they spread out. But why is that? Why does that mean that entropy increases? Now, for simplicity, I'm gonna go ahead and oversimplify that all the molecule bonds in your coffee cup are the same. So in this example, a microstate would specify the position and velocity of all the atoms and molecules in the coffee, whereas a macrostate would be an arrangement of the milk molecules. And you can think of this as a group of energy configurations. Each macrostate has a corresponding probability, and for the macrostate on the left here, for example, the all milk on one side macrostate, there's a number of arrangements of milk molecules so that all the milk stay on one side. They can shift a little, switch positions, but this number is much, much less than the number of arrangements for the milk to be spread out, like on the right. And so we say that this spread out milk macrostate has higher entropy. And again, that's simply because the molecules have more space to move around. There's way, way more possible configurations for the molecules to arrange so that they spread out. And that leads to higher probability. So, to sum up this slide, what we know now is that entropy is really a property of macrostate, and it has something to do with the number of possible configurations for that particular macrostate. And that leads us to Boltzmann entropy. The formula for Boltzmann entropy has simply this Boltzmann constant k sub b, and then a term that I hope you recognize now is the expected value of the negative of log, I should put a negative there, of the probability that a microstate I is occupied. And to simplify this formula, if we assume that each microstate is equally probable, so all these PIs are the same, then we can simplify this as kb log of omega, where omega is the number of configurations for that particular macrostate. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time and is constant if and only if all processes are reversible. Now, I like to think of this law via this quote by Brian Cox, who says, entropy always increases. Why is that? Because it's overwhelmingly more likely that it will. So just like your milk and coffee example, because there are way more configurations for the milk to be spread out, it does. So that was Boltzmann entropy, which is the specific case of Shannon entropy. In Boltzmann, you focus more on the physics macrostate. Shannon entropy, on the other hand, developed in information theory, measures the expected value of self-information. The source coding theorem, which we're not going to go over today, states that the Shannon entropy of a model is essentially the number of bits of information gained by doing some sampling on a system your model describes. The formula for Shannon entropy is very similar to what we've seen for Boltzmann entropy, except we now don't have any more Boltzmann constant, and the log is now log base 2. And we notice that first Shannon entropy is denoted as H, and P of x of I is the probability of the possible outcome xi, and the log P is really there first to make the source coding theorem works, but also you can think of it, the negative log, as a measure of uncertainty or surprise. Okay, so let's take a look at an example. I have rewritten the formula for Shannon entropy up here, and the source coding theorem here, just to again emphasize that you can really think of Shannon entropy as information gain. So if we take a look again at our coin tossing example, the question is, what is the Shannon entropy of this coin tossing action? So again, it is defined on a random variable x, and if x is the sample of the next coin toss, what is the information gain? We can plug this in the model, right? We have only two outcomes, heads or tails. So we just plug these two p's in our summation here to get negative p log p, and then plugging these 0.5s for probabilities, we end up with 1. Does this 1 make sense? Do we gain 1 bit of information by tossing this coin? Let's think about that for a minute. Beforehand, when you know that the coin is fair and we have 0 bit of information on whether this is going to come up heads or tails, right? So after tossing this coin, you know exactly what the value of this sample of the random variable x is. You have gained 1 bit, and that's why Shannon entropy is 1. So that makes sense. Now, that's one example. What if, again, we have a different coin that is not fair? In this case, what if it always comes up head if p heads equals 1 and p tails equals 0? Plugging these numbers in here, you get entropy of 0. Now, I'm not going to talk about the limit of p log p when p approaching 0 from the right, but it does approach 0. And similarly, if we have the other way around, when p heads is 0 and p tail is 1, the entropy is also 0. Again, let's think about this for a little bit and see if that makes sense. Does it make sense for a coin toss to have an entropy of 0 if we know exactly what is going to end up? And the answer is yes, right? If you know that the tail is completely biased and p heads is always 1, you know that it's going to come up heads in the next toss. You gain 0 information. So I hope that makes sense. And I just want to do this quick plot of p heads on the x-axis and entropy on the y-axis, and it's going to have this curve from 0 to 1, and then highest at 0.5 here. We're going to see this plot again later, so I just want to point this out now. There are other quantities in information theory that could be very important, especially for application. Again, rewriting the entropy formula here, negative p log p and some of that. Joint entropy measures the uncertainty of a set of variables simultaneously. So in this case, we have two random variables x, y. Joint entropy measure the uncertainty of both of those x and y. And so the formula is very similar, except you now have a double sum of the probability of both of these value x and y happening. Okay, and conditional entropy quantifies the amount of information needed to describe the outcome of x, given that the value of another random variable y is known. So the formula for conditional entropy looks a little bit complicated, but it's really just the joint entropy subtracted by the individual entropy of the variable that you're conditioning on. Mutual information is a measure of mutual dependence between two variables. And again, we have a formula here for mutual information, which is the independent entropy for each of these random variables subtracted by their joint entropy. You can also rewrite mutual information as the Colab-Liebler divergence of these two distributions. Now, a quick digression. The Colab-Liebler divergence, or the KL divergence, is defined on two probability distributions, and it measures how much one distribution diverges from the other. So this is a formula for it. As you can notice, this metric is not symmetric. The KL divergence of P given Q is not going to be the same as the KL divergence of Q given P. So just keep that in mind. It can also be extended to continuous and random variable as well. And finally, cross entropy has a very similar formula with the KL divergence, except instead of a P here, you have a 1 on the log. And it tells us the average length of a message from one distribution using the optimal coding length of another. That's a little bit technical. I'm not going to get into that now, but I will give you resources to read up on it later at the end of the lecture. Okay, so what are some applications of information theory? The first that I want to mention is it can be used to measure interaction effect between two variables on a certain outcome. So if you take a look at these two variables A and B and the outcome C, the interaction effect is defined as the mutual information between AB and the outcome C, and AB is the joint attribute constructed from these two individual attributes A and B, and subtract that term by the information gain about the outcome C when variable A is known, and similarly information gain about the outcome C when B is known. Okay, so you can think of this as the gain in the outcome obtaining by considering A and B jointly beyond the individual effect of each of these variables. Okay, so let's try this out. If you go to tinycc/mutual info, in this Colab notebook, we're gonna calculate the independent effect, the total independent effect and interaction effects between the variables and an outcome. But first, let's go ahead and install this MDR package. We're going to need pandas to read in our dataset and also utils from the module MDR. Let's go ahead and do that. Read in the data here. We're going to set Z to be the 0th column of our data frame. So what that means is that Z is this first column here. What does this data frame represent? Each of the rows, you can think of them as a participant or a patient. A class of 0 means they're healthy, 1 means they're sick. X0 through X9 represent 10 single nucleotide polymorphisms or SNPs in our data set. And the values 0, 1, or 2 represent the number of minor alleles for each of these SNP. And finally, we're going to use mutual information function in utils and also two-way information gain to calculate. So this mutual information is going to be between any column and our outcome Z, whereas the two-way information gain is going to be between any pair of columns and the outcome Z. So if you run that, you're going to see that you're going to get the final total mutual information. 1D means this is independent or main effect, and 2D is the interaction effect. All right, so let's head back to our slides and talk about some other application of information theory in genetics. And so first we have GAIN, which is the genetic association interaction network that builds edges from interaction information. We have SNP rank that ranks SNPs based on the centrality metric that combines main effects and interaction effects. And finally, regain, which is the regression model for epistasis network. Epistasis is essentially just a term that used to indicate the interaction effect or the epistatic effect in genetics. Another application of information theory you're going to find is in machine learning when we're trying to calculate the node purity to get at feature importance for tree-based machine learning models. So I'm not going to get really deep into the Gini index and misclassification errors for feature importance, but again, I just want to point out that that curve that we talked about earlier for entropy is here. And if you want to see more details on how these different measures affect the feature importance, you can go to the this Elements for Statistical Learning book and see more details there for all of these formulas. But to illustrate that, let's get to a decision tree example. If we let S be a sample of training examples, and P plus is the proportion of positive examples, P minus is the proportion of negative examples in S, then entropy would follow this formula. Again, what we have seen before, and it measures the impurity of S in this case, if S is a sample of training examples. So how do we know if a decision tree is good or bad, or how do we compare between two? We're going to look at the information gain or the entropy decrease that a particular decision tree gives S. And formally speaking, the gain that you get for a decision tree on S is going to be the difference between the beginning entropy, which is the entropy of S, and the end entropy, which is the entropy of each of these leaf nodes in the decision tree scaled by the size of the nodes. Okay, let's take a look at a concrete example of S. Say S has 9 positives and 5 negatives. That means we have 14 samples in total, and so P plus would be 9 over 14 and P minus would be 5 over 14. And we can easily calculate the entropy of S with the formula that we've seen before. Here we have just plugging in these P plus and P minuses, we end up with about 0.94. And remember, entropy goes from 0 to 1, so 0.94 is actually pretty high. We do have a good mix of negative and positives in this training sample. And so if we now try to compare these two different models or classifiers, the first one is based on humidity variable, and the second one is based on the wind variable. These variables don't really matter much. What we really worry about is the end node here, the leaf nodes. And for this particular leaf node, you get an entropy of 0.98. For this one, you get an entropy of 0.59, which is actually a lot better than what we saw earlier, and similar here. But how do we know which one is actually better? What we do is we use this formula calculating the information gain based on each of these models. So the gain by applying the humidity model on S would be 0.152. And the gain based on the wind model using the training sample S is 0.048. And that means that we're going to gain more if we use this humidity model to make this cut in the sample. Okay, so that's all I have for you today. And if you're curious about any additional resources, want to read more on entropy or information theory, I highly recommend these set of lectures by David McKay. The Elements of Statistical Learning gives great applications. Wikipedia, of course, is a great source. And also I highly recommend this Visual Information Theory blog post by Christopher Olah. He did an amazing job of explaining information theory and entropy in really easy to understand term, and he got into like the code words and the lengths and optimal way of transferring information and things like that. Highly recommend it. And I'm gonna end with this quote by Chekhov: "Only entropy comes easy." Thank you.